Okay, so yesterday we looked at numerical and graphical approaches. Today we'll look at analytical approaches. Now, I don't want to go into too terribly much detail with this because a lot of what we're doing right now is going to be superseded by a technique called L'Hopital's rule, which we'll learn once we know how to take derivatives. And it makes short work of a lot of these limits that we're going to kind of have to grapple with today. So we don't need to become experts with this because there is a better technique. But I want you to understand it and understand kind of how we could analytically answer these questions. So evaluating limits analytically. First of all, this means without tables or graphs. The advantage of this is it's going to give us exact answers, not decimal approximations. We'll get an exact answer right off the bat. To do this, we need to first, and this is kind of what I want to focus on mostly today, is just some properties of limits. We just want to there's some simple limits that we just know we don't have to really think about very much. So we learned already that the limit of x as x approaches c does not depend on the actual value of the function at c, right? We never get there, right? However, it may happen, and in many cases, the limit does coincide with the value of the function, and those are the easiest kind of limits to take. These are the kinds of limits where the ant anticipates stepping on the place where he actually would step. If he made it to x equals c, he anticipates stepping on the place where he would end up, right? What's the easiest way to answer the question, where does the ant anticipate stepping for a function like that? What do you think? If it's a type of function where there are no tricks, the ant is going to step where he anticipates stepping, what's the easiest way to answer the question, where does the ant anticipate stepping? Direct substitution, because it's going to be exactly where he does step. So the easiest way to answer the question, where does he anticipate stepping, is to answer the question, where will he step? Right? Does that make sense? Okay, that's where direct substitution works. Here's an example of that. Like if we have the function f of x equals x squared. Well, what's the limit of x squared as x approaches 7? 49, exactly. Because where is the ant actually going to stand on that function at x equals 7? 49, but that's also where he's going to anticipate stepping. Agreed? What are the only reasons that an ant would not land where he anticipates landing? If you think about it, that's kind of a goofy setup, right? That would have to be something where there's a hole in the function, or the function is defined as a piecewise, something weird is going on there, right? There's a place where either the function has to be defined in a crazy way, or maybe the function is undefined at a point, something like that, right? But this is just a plain old function whose graph is continuous, right? And so there's no tricks up our sleeve here. The ant is going to step where he anticipates stepping, so it's easy to figure out what the limit is. Piece of cake. That's a direct substitution question. We always want to rely on direct substitution whenever we can because it's super easy, okay? So we'll try that. And there are some basic limits that just rely on this. Now, what about this one? Does this make sense? What's the limit of the function b as x approaches c? It's b, but why? Explain that. And there's a couple different ways you can think about it. But we've been talking about graphs, so think about it in terms of a graph. How about? What does the graph of y equals b look like? What's the graph of y equals b look like? Horizontal line, right? B is a constant, right? It just looks like this. So as x approaches any value, we'll call that c, where does the ant anticipate stepping? At what y value? Hey, oh, you got it?
Is now good or later?
Would it later be okay with you? Are you going to be around here? Okay, awesome. Thank you. Doesn't matter. The y value is always going to be b no matter where, right? Easy answer. What's the limit going to be? The only possible limit on the only possible value on the entire function y value, which is b. So a piece of cake. How about this one? What's the limit of the function x as x approaches c? What do you think? Think about it in terms of a graph. What does y equals x look like? Yeah, okay, so here's what is it again? Y equals x. It's a line with a slope of 1 through the origin. Yeah, it just looks like that, doesn't it? Okay, so now as x approaches c, what's the y value going to be? Yeah, right? If x is 10, what's the y value on the line y equals x? 10. Okay, so it's approaching the point with coordinates c, c, and so yeah, the output is going to be c. Okay? The other way of thinking about that is just use direct substitution. If I plug c in for x, what do I get? C, right? What if I use direct substitution here? If I plug c in for x, I get b because there are no x's to plug it into. Okay? And then if I take any function like x to the n, as x approaches c, isn't the output value I'm approaching just going to be c of n? Again, just apply direct substitution. I plug in c and I get c to the n. Okay? So those are all straightforward. Super easy. Those are ones that we just know. What are some other things we can do? Okay, there's some important properties here, like, and I kind of want to do these. This is the way it is in the textbook. I think this is easier to see. Okay. They mean the same thing. If I have the limit of b times f of x as x approaches c, there's a property which just says I can pull that constant out in front of the limit. Okay? And the answer is just going to be b times whatever the limit of f of x is. Okay? That's a really handy, and you could easily convince yourself why that is. I'm just multiplying some function by b to stretch its amplitude. So if I take the limit of the function f of x, well, I'm going to multiply it by b because the y value has been multiplied by b. But it's just a property that you're going to use. We use this all the time in calculus. I can pull scalar multiples out in front of limits. Later on, we'll do the same thing for derivatives or integrals. Okay? What about one like this? What if I've got the limit of a sum or a difference of functions? You're able to do this. Here's a property of limits that makes it really handy. I can split those into separate limits and deal with them one at a time. So I can take the limit term by term, one term at a time. Everybody see the advantage of that? So for example, if I'm doing the limit of x squared plus sine x as x approaches 18, I can take the limit of x squared as x approaches 18 and the limit of sine x as x approaches 18 and just add them up. Okay, piece of cake. If I'm taking a limit of a product of functions, very conveniently, I can split those into separate limits and take the product of whatever those limits are. Okay? I don't have to treat this as a limit of some great big thing. I can take it into smaller pieces and then multiply the results. Okay? Do the same thing with quotients. As long as the limit of g of x is not 0, and I don't divide by 0, I can split up a quotient the same way. And I can do the same thing with a power. If I've got the limit of f of x to the n, I could just take the limit of f of x and get an answer, and then take that answer to the nth power. Okay, give me thumbs on that. Does that make sense? You get lots of practice with this, but those are nice properties that make it easier for me to evaluate some limits analytically. Okay, so what would I do here with a polynomial? Yeah. What would I do with this one? Yeah, what's 4x squared as x goes to 2? 16. Limit of 3 is what? 3. So what's the answer? That's it. Just when you're evaluating limits of polynomials, just evaluate the limits term by term. Piece of cake. Just do that. Okay? No big deal. For your notes, there it is. Do you have to write it out this way? No, it's too much writing. Just do it, just, you know that what you're doing is you're just taking the limit term by term, but you don't want to have to write out separate limits. That's just awkward to have to do all that writing. You want to be as compact as you can in your notation. Okay, what about rational functions? We already talked about that. Rational function, I can just evaluate the limit of the top and the limit of the bottom separately, which means I'm just going to get whatever I get on top and whatever I get on the bottom. An easier way to think about that is you're just going to use direct substitution. Okay, so for example, how about this guy? What's the limit of this rational function as x approaches 1? That's 2. How'd you get that? Direct substitution. I'm going to get 1 squared plus 1 plus 2, which is 4 in the numerator, over 1 plus 1 is 2. 2. Anytime you have a rational function, as long as you don't get a 0 on the bottom, just directly evaluate. Piece of cake. Okay. Same thing's true for radicals, right? If I want to take the limit of the nth root of x as x approaches c, just plug it in. Evaluate directly. It's going to work. What about the limit of a composition of functions? Okay, this is one we got to talk a little more about, but it's totally intuitive. If I hadn't even told you this, you could have taken a limit of a composition without even knowing that this was a property, I promise you. If the f and g are functions, if the limit of g of x as x approaches c is L, and the limit of f of x as x approaches L is f of L, then the limit of f of g of x as x approaches c is f of L. Right? How come? Because you work from the inside out. Okay? I'm going to do the limit of f of g of x is equal to f of the limit of g of x, which is just f of L. Okay, I'll show you how easy that is. It seems complicated, but let's do one like this guy right here without even doing part A. What's the limit of the square root of x squared plus 4? You're going to do it exactly the way you would think you would. Where do you start with that? Direct substitution, and you're going to start by order of operations. You start inside the function, right? Okay. So if I plug 0 in, x squared becomes 0, so I get the square root of 0 plus 4, which is the square root of 4, which is 2. Big deal. The only point of that whole the property I just showed you is that you have to start from the inside of a limit. Okay, effectively, that's the outcome. What about this guy right here? We don't even have to think about this in two pieces. We just directly evaluate, start following order of operations, starting inside the function, working from inside out. As x approaches 3, what's 2x squared? 18. Yeah, 2 times 9, 18. Minus 10 is 8. Cube root of 8 is 2. Done. See how easy? Evaluating limits directly couldn't be easier. It's just very, very intuitive. And the same thing works for all the trig functions. You would just evaluate all the trig functions directly until you run into a problem. And we'll deal with those later. Okay. Like these aren't even really worth going through. I just would evaluate all of these directly. Just plug in 0 and see what you get. Okay? And in fact, we're going to see a pattern here. In all of these examples, direct substitution worked. We got an answer, done. What if it doesn't work? So here's our strategy for finding limits. Attempt direct substitution first. It's probably going to work, and you're done. There's 3 possible outcomes. Yay, it works. You're done. You get an answer. If it's a rational answer, it's going to be of the form A over B. Wouldn't have to be rational, right? But even if it's irrational, we could make an irrational fraction out of it with irrational numerators and denominators, right? We get something like that, okay? That's one possibility, where B is not equal to 0, okay? We don't get 0 on the bottom. All the previous examples were like that. We got answers. Okay, what's the first thing that could happen that throws a wrench in the works? First thing that could happen is we get an answer where the limit of the numerator is a real number, but we end up with a 0 on the bottom. Okay, we actually have seen stuff like that. That was the example where the function went up to infinity. That would have been one like this. Okay, what did we say about that? Well, for now, we just say it doesn't exist. Right, we can say a little bit more than that in the future. We even did say a little bit more. We said we could say it's infinity. It doesn't exist, but we had a case where the limit was infinity because ants from the left and the right both anticipated climbing to infinity. Okay, those are really no big deal. I mean, we're done. We know it doesn't exist, and maybe we get consistent behavior, and so we can throw an infinity in our answer, but we're done with the problem. Okay, here's the third type, though. The third type is a little problematic. Here's a quick example of the second part. I've got the limit of this rational function x minus 5 over x plus 2 as x approaches negative 2. And I get the answer negative 7 over 0, which means it doesn't exist. Okay. And we'll explore this more closely when we focus on infinite limits, maybe saying a little bit more about that, but we can't say that much more about it. Okay, here's the third type. You get an answer like that. Okay, you guys have already gone through, I mean, depending how far you got with the Khan Academy or how much of it stuck, can anybody talk to me about this? What does this mean? Jimmy, you threw this word out the other day. How would you describe that limit? Indeterminate. It's an indeterminate form. If you get a limit that works out to be 0 over 0, or it could be infinity over infinity, we'll find later on, or it could be 0 times infinity, or it could be infinity minus infinity. There's a host of different, we about done? Okay. There's a host of different kinds of outcomes we can get that are indeterminate, which just means more work somehow. We've got to come up with a way of resolving that indeterminacy and getting an answer. And that's what the focus will be over the next few days for us. How do we do that? Okay? All right, good place to stop.